So what is Concoction? Concoction, as our README states, is a shared Java malware scanner capable of static and dynamic analysis. That is pretty short, so is there any extra detail? At the moment, not really on a public README, but plan-wise, here's the gist of what we have. The static analysis will basically be the amalgamation of different tools that we've made throughout the basically campaigns of Fracturizer. So tools such as netcode detector, JSUS, JNeedle, and I think those are really the big three that we're looking at. But anyways, those all are static signature scanning based tools, and we're going to be taking what we've learned working with those and try and incorporate them into a single bundle in a way that is easy to configure for different users of different environments. So you could either be an end user who's running just a Minecraft launcher and you want to check your mods and your mod pack if they're safe. We'll have a quick and easy to use static scanning thing for that. We'll have it'll be the same, but for everyone, it's just you can integrate it differently. So the end user would run it as like a separate jar file program. Mod hosting platforms can use it in their automated upload so that when a mod developer uploads their mods, it runs it through Concoction, creates a report, and then if there's eyebrow raising indicators in the report, manual review kicks in, and then the mod will be postponed until manual reviews gone through. So that's the static portion of it. It's, again, quite simple, basically a improved version of what we've had in the past, but easier to configure. I'll get in more on that later. And then there's the dynamic portion. The dynamic portion is essentially going to be virtualizing the Java code in these jar files, running them in a sandbox, which I can explain more later. And we will not be matching instruction patterns per se, but we will be able to basically interject and check what the parameters are for basically any call in the entire JVM ecosystem that these mods are using. So a quick example would be if you're using base64 decoding and you pass that to, let's say, runtime.exec. Runtime.exec will take in a string and evaluate it on your host machine. So if you wanted to do, let's say, delete a file, you could do runtime.exec rm-rf star. And that would delete everything in the current directory and everything in those directories, etc. Now, because it's base64 encoded, what you would see is runtime.exec base64 decode and then a bunch of gibberish. Now, static analysis can detect things like this, but you got to consider base64 is only one way of obscuring that string that's going to be evaluated. There's an infinite number of possibilities you can do because you can create your own encryption scheme for strings relatively easily. So all it would take to defeat a signature match there is to just change the string encoding. So the approach to that is to use dynamic analysis. Now, if you're going to be running some code, the system needs to actually know the values for the stuff to work. So in our sandbox, we will run that sample bit of code that I mentioned before. It will decode the base64. It'll load the base64 class in the sandbox, load the string, pass the string into the base64 decoder, decode the string. We now have that value. It will then pass that value to runtime.exec. And then we now know runtime.exec is being passed the string value rm-rf star. Now, it won't actually execute anything because our sandbox fully controls everything, and by default, everything's locked down. There is literally no way for the default implementation to access the host file system because the way that the sandbox works is that it effectively will interpret all the JVM bytecode, but anything that goes out of the JVM, so, like a native function that hooks into your operating system, like, the way that Java has the file system implemented, there's different native implementations for Linux, Windows, Mac, etc. Well, our sandbox doesn't know any of those, and it's not going to just trust them. So when you get to that point, it fails. So what we do in our sandbox is we go through, we read these implementations and recreate them ourselves and point them to our kind of like an interception API for file I/O. And we can fully control all of that. So we can log all of the file interactions that are happening there, all the things that are being passed to runtime.exec, etc. But none of it actually goes through to your host machine unless you explicitly allow it to, which, why would you? But that in mind, because you have the insights of the actual program running, you don't need to worry about any of those issues that I described before with string encryption, because to pass and run the rmrf command, string has to be decoded. So no matter what, as long as the application is written in such a way that that string is consistently decoded, you're going to be able to decrypt it. So that is why we have both the static and dynamic analysis capabilities. Static one's faster, but the dynamic one is more flexible and will be able to detect more with less configuration by the end users. We will provide a host of likely defaults, I imagine. Now, that is the general overview of the project. Next, I will be going into the actual code of the project and summarizing what different pieces of it are, how they work, and if you're a developer, maybe some pointers on what we want to see going forward in case you want to contribute, something like that. Okay, now for the long section for developers. I have the project open in IntelliJ, and I'm going to be going over the build scripts first, the modules, what they're for, then going into the actual code of those modules. So getting right into it, build script stuff. This is the root build script. It handles setting information that's common to all the other build script modules. So it just sets the version stuff, sets up some basic Java things, and lets it so that all of them can pull dependencies from basically little shorthand names that we've defined in this dependencies file here. All of our versions are managed with these variables, so updating is pretty simple. And that's really all that you need to be concerned with here. We have incremental compilation, targeting Java 8, and this is our test setup. Basic, simple stuff. We have two modules, the library and the app. The library, we're just naming concoction node-lib. The lib name in the path is so it's clear intent as a developer looking at it in like a file system. But the Maven artifact we're publishing, we just want to use the short concoction name, so that's why the name is configured like that. The library, of course, the API stuff. The app is the command line interface stuff. The command line interface is defined like this. We have Pico CLI for command line population stuff, and the rest is just kind of bullshit dependency management stuff. So pretty regular stuff going on here. There's not really anything here right now because the API isn't solidified at the moment. So that's basically it for the API in terms of app stuff. Not really much going on there. Next, we have the library itself, and there's a bit more here. So we're using gversion, which is a plugin that generates a file that details a bunch of build information. So this is our Maven artifact group, the artifact name itself, the version that we're on, the number of git commits that we've had on the project, the hash of the current git commit, the date that the commit is made on, the branch it's on, the date of the actual build in both, human legible time and Unix time. And dirty is for if there are local changes that are beyond this. So if I have a local change that is not from this commit and I haven't published it yet, this will be 1. So I have stuff I'm working on, so it's 1. So that's gversion. We are a Java library. This is just test stuff. And the Maven publish plugin lets us easily bundle a bunch of files in such a way that we can easily pass them along to Maven Central in our CI script. So here are our dependencies. The API ones are ones that if you're consuming this as a library, you will be required to use in your project. And the implementation ones are ones that you won't be. Now, they're going to be cases like this where we define this as implementation, but that is because we are shading it in. Because as a library consumer, we do not expect you to have to add the Jetpack repositories. So what we're doing with this is anything that is not in Maven Central, we're shading into the project itself. Eventually, because I run this project, I'll be moving it to Maven Central. There's just a number of things I want to address first, so that's a to-do item. And then SSVM is not made by me, it's made by Xdark, but I am a contributor, so I can control some of that. I can't control publishing to Maven, but I can add different APIs to it, but that's besides the point. So SSVM is something that I think will have to be shaded in, but that's not really a huge concern. The only thing that's a to-do note here is that we don't want to use the shading setup that we have now. We want to eventually migrate to a proper shade plugin, but without minification. Minification is bad. So that is the dependency stuff we have in our project. This is the version automated file thing generated. That's config. This is a function that lets us only generate this file when it needs to be generated. So this is the version up to date essentially. If this did not exist and we always did that, the incremental build system would always fail. So you would always do a full recompilation. So that's kind of important stuff here. And then this is our publishing section, which generates the POM file and additional Maven metadata. So the only thing you'll ever want to change is this developer section. If you are contributing more than, a small one-off change like fixed typo, feel free to add yourself if you contribute something significant to the project. If you do, you'll want to do that here if you want to be included in the Maven repository release information. So whenever you make a module in Maven, it tells you who the authors of those things are. So that's where you do that. You also want to add yourself in the authors list here for JReleaser. This is really only for GitHub releases, but I mean, I guess you could add yourself here. The main one is here. And then this is more, Maven stuff. You don't have to, it's all for CI. Don't worry about it. CI stuff, and CI stuff. Cool. Moving on. Now we have the actual code of the project. So we have our info MMPA, say that 5 times fast, concoction package here, and we have some packages. The one that you may want to start with is input, but I think it's best to start with model. In the model package, the main thing is this application model. As it says, this is the full application model comprised of one or more units. So a unit is essentially just going to mirror a jar file, which is exactly what we say here in our model. And the primary model is going to be the file that we're analyzing. So for scanning mods, this will be the mod jar files, and the supporting resources will be any of the libraries that they depend on. So this is mostly for dynamic stuff. I'll get to that later. But yeah, this is just going to model a jar file, model the libraries of the jar file, and these are utilities for manipulating and reading information from these in a different way. So that becomes relevant later. To build such a model, you'll use the model builder. There's a static builder down here to create a builder instance, and all you need to do is pass along paths to jar files that you want to read, or byte arrays containing the bytes of jar files you want to read. And you'll have to name each one with a unique string. So this is for file paths, it's going to be the file name itself. But because it's a raw file and we don't know the name of the file, you got to give that to us. So the way that these are implemented is it's going to create this model that represents the classes and the files in a jar file. So anything that has a .class and is a valid class file that can be read goes in this map. Anything else is a file, and it goes in here. So we read the input, create an identifier for the file name, add it to the model. Same thing for the one, except we use the identifier that you give us. Then to build it, it slaps them all together, and bam, you have your application model. So that's essentially all the I/O you need to know. If you want to go more in depth, most of the stuff isn't really in this model type. It's in these impl and archive directories. So going over the stuff in here first, the way that we add classes is that we verify that the byte array represents a class that can be read and written back with ASM. That's kind of a litmus test to get rid of any maliciously formed class files or things that are named .class but aren't. So simple check there. And if it fails that check once, we try and strip out illegal junk that confuses ASM, which is the bytecode library we use. So we're using CafeDude for that, the library I make. And if it patches it and it goes through, then we know, okay, cool, it is a class file. It's just using junk to crash ASM, which is suspicious as hell. We'll eventually want to make it so that content that is added like this is immediately flagged, but to-do item. Anyways, if it's not a class, we throw this exception, and when you handle that here, if it fails that throws exception, we just add it as a file. Here's our verify logic. We just read it, we write it back, and if it works, we will get to this code. If it doesn't, exception's thrown. Pretty simple. So that's basically this model type. Then we have the actual archive readers. So typically you'll be working with these archive load contexts. It's just an enum, and the different values are for how the archives are to be read. That is because the JVM has multiple ways of reading jar files, which is a big point of confusion. So the way that it works is if you have a runnable jar that you run with java-jar, so like an independent program that you're running through these commands, you want to use this one. If you're loading content through the zip file or jar file APIs, I'm assuming this is what most of the mod loader frameworks are going to be using. You'll use the random access jar one here. And for some reason, if you're using the input stream or jar input stream methods, use this one here. And they all point to the archive reader implementation types, as you can see in this constructor here. And then the reader gives you that. So looking at that file, this outlines how to read archives into that model type that I was going over before. And different child types do it different ways. So we have some base logic here, and we have some common logic here. So the way that those are implemented, those abstract ones, is they're using my library LLJZip that me and a bunch of other contributors have added stuff to handle different weird edge cases that different JVM contexts use to handle zip file loading. So me, Xdark, Ned, a couple others. But yeah, this is we're using it this way because this will let us use a singular API for interacting with zip files while maintaining the ability to replicate the behavior of the different zip file parsers that we want to support. So for random access, you use the zip.io read standard. For the runnable, you use read JVM, and for the streaming one, you just use read naive. Now, they will occasionally have their own custom handling, so there's some filtering logic going on here. That's just to normalize some things in terms of like how the behavior should replicate those APIs. And there's some additional stuff here. There's some to-do notes, but if you want to contribute to getting the to-do notes finalized and fixed, go on ahead. But for the most part, this is basically complete. So that's how we handle zip files. And then those are called from these input readers, and these input readers are referenced in the model builder here, which we were going over before. So that kind of summarizes how you create this application model all the way from how the actual jar files are read and parsed. So the next thing you'll probably want to go to is the scanning. And to start off, I think we'll start with the models. Yeah, let's start with the models. So for the standard ASM scanner, we only the only model types we have implemented so far for that. The dynamic one, we have some code laid out for, but we don't have any model information for that yet. That's pending, and that'll go in this behavior package. Anyways, for the basic ASM model, we're looking for this one. This model represents a single detection archetype, so like a family of malware, for instance, and it can have one or more different variants that indicate that this archetype or this malware family is found. So the archetype just kind of outlines what the thing you're identifying is and how sus it is. There's not actually any detection information here. And then the variants actually are the pattern matching component of the model. And this is just all basically Java boilerplate. You can create the models from a JSON file. You can either pass it along as a file path or as a string literal. The matching logic is contained here and here. There's some advanced stuff that you can go over, but you don't really need to know much of this. Just know the actual like model types. So going over that, we have this list here, which is just a list of this outline and instruction level matching. So the way that the model works is that you have a list of per instruction matches. So if you want to make a pattern match for something suspicious like runtime.exec, you would probably have 2 to 3 instruction matches, depending on how the bytecode's laid out, to match the parameter of exec and the execution of exec. I actually have an example that we can take a look at real quick here. So we have the matcher for runtime.exec. We're going to match the get runtime and .exec calls. So the way that that works is there's a static reference to runtime.getRuntime. So that's this. Then there's a string that we're going to load. It can either be from a local variable or a string constant. In this case, we're using a constant with load constant. That's the LDC instruction. And then we're going to be looking for the invoke virtual call to exec, which is runtime, blah, 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 exec, and then it returns a process. We don't really care about the return type. We're just, this. So that's our match. Pretty simple. Alternatively, let's say you had some code in between there. You can use a wildcard syntax here like that. The way that the wildcard system works is that if you want to match one wildcard instruction, you have 1 star. If you want to match any number of specific instructions, you have a number here like 5. This will match anywhere between 0 and 5 wildcard instructions. And if you want any number of any possible wildcard matches, you just use 2 stars. So that can be an infinite amount of instructions between this one and this one. But otherwise, it's the same setup as this. And then you may have thought, okay, well, what if, like I said before, the string comes from not an LDC, but a variable? Well, you can use this. I'm not using it for that. I'm using it for this, the way that we get the runtime. So the way that this works is that this is an instruction, this is an instruction, and this entire block is an instruction. The way that that works is that this is one instruction match, but it can be any one of these sub-matches. So we can match this one or this one, and that counts as one match. So let's say we had our runtime stored as a field somewhere. Then we're going to be using a get field instruction on that, or a get static instruction, either one. That's why we're using starts with get, because get static, get field, they both start with get. And then we want to check if it ends with runtime, because that's going to be the field type. So that would be how you would handle a field reference to the runtime value. And this is how you'd handle any kind of method call that would yield a runtime. So either of those options that give you a runtime, and then we have our same kind of thing from before. Then there's this last one, which is just a check cast. So like if you had an object, but you didn't know it was a runtime, you could cast it to runtime and then call the thing on it. So that's just like another example. There's plenty of more variants you can add here that would match this logic. It's just that this isn't purely an example. So how does this translate to this interface? Because this is pretty bare bones. Well, that is because we have some custom JSON deserialization going on here, and that can be read by going through this code here, but I'm just going to point you to those classes. So first we have our instruction match, which is pretty simple. That is this class here, instruction implements instruction match entry. You have an opcode and arguments that you can match against, and for both of those you can match different ways. So if you saw before, we have equals and we have starts with. The operations for that are defined here, where you have equals, contains, starts with, ends with, regex full match, and regex partial match. So all of those should be relatively self-explanatory. The way that it works is that this one matches against the opcode, this one matches against the arguments. And the way that we get the opcode is we're just toStringing the opcode name. So get static, the opcode like, I don't know, like 37, which maps to the name get static. Simple name mapping, all caps. So that's why we have equals invoke static in all caps. Then the arguments is basically we're going to be using a Java a bytecode assembler library to represent these instructions in a text format. We're going to chop off the opcode and use the rest of the data in this argument section. That allows things like this invoke static call to get the static name of the method here and then the return type. This is generally how most of those assembler libraries represent the invoke static stuff. Kind of the same thing with this field, yeah, because this is field stuff. Can get into that more later, but the general idea should be relatively clear, and there's some nice Java documentation here if you want to read that. Next up, we have a bunch of other implementations. In our example, the next thing we have is this wildcard. And for that, we have instruction wildcard, which just matches one single instruction. So that would be 1 star. But if you have 2 stars, that is instruction wildcard multi, which matches one or more instructions. Now, the way that this works is that you can match any number of those, which we have a special case here. If the count is not positive, yeah, it'll match any number of items. Otherwise, it'll match the given count. And the given count, just as a reminder, is just the number after the first star. So this would match 0 to 3 wildcard instructions. This would match 9. Now, you could also do -1, but that would just be the same as 2 stars because of what I just said. So that's this. It's pretty simple. Then we have the section here, which lets you do multiple different options for a single instruction match. And that is handled with this multi-instruction. And this is the abstract base. So you have the option to use any, which will take a list of options. This can be any of the instruction match entry types, so any of those. It can take any one of those, and as long as one of them matches, it's good to go. Then you can do all, which at first glance may seem silly, but there are situations where that works, mostly for regular expressions. If you want multiple regular expressions to match and you don't want to like make a really complex regex that accounts for both cases, you can use 2 that both have to match. So that's this one. And then the last one, which is none. So none may seem a bit silly, but actually it's just a simple inversion. So if you have a API that is, let's say, mostly suspicious in terms of how it's used, but there's 1 or 2 calls that are okay, what you would do is you would define those 1 or 2 calls that are good, and then use this not, so this none matcher. And then the way that would work is that if any of the suspicious calls are used, it would not be the 2 or 3 good calls that you've defined, which in turn would actually make it match. So if you have a case where matching the things against what does not exist is easier than all of the options that do exist, use this. And for now, I think if we check the subtypes, that is all of the instruction matches we have, because that's really all you need, I think. Most of the, there's a few additional complex cases we may add in the future, but most of the basic stuff's there. Now, the way that this is actually handled in our scanner is you pass along the models, which are, again, just the signatures that you want. So, like, each model is essentially one of these files. And you pass it along here, and then you can scan any application model that you want with those collections of models. So it's going to iterate through all the classes in the model, and then individually per method, run those models on them. So you can see we loop through the classes, we loop through the methods, and then if the method has code in it, we're going to match those models against the code in the method. And that's where this happens. So another instruction check, make sure there's code. Then we start matching the variants in the model. So for each variant, we're going to make sure that works. Short, simple way that this works, there's a lot of, I mean, there's not a lot of code here, but the way that it works is we start at the first index of the variant and we check if that matches. If that does match, we increment and go to the next instruction matcher. And if that matches, and we go through to the very end, then this condition is true. We've matched everything in our variant, and we report that we have made a detection. Then what we do is, after the detection is made, we jump back to where the initial match was made, so the first instruction where that was, and then increment by 1. That way, if there's multiple different variants that overlap in the code, you can signature match both of them at the same time. It's not technically necessary, but for just the sake of correctness, I think does make more sense. Now, there's more than just that. Of course, we have wildcard support. So the way that that works is that we allocate a number of allowed wildcard usages, and as long as you can go through that, you're good to go. The loop continues. But if you exceed the amount of allowed wildcards you have, we do the same thing that we do with the matches made, but we revert back and we don't have any matches. That way, if you had like a partial match and then the wildcard failed, it would jump back. Same reasoning as I said before, in case there's like overlapping in the variants. And this is how we allocate the allowed amount of wildcards. The single one gives you 1, and the multi one gives you multiple depending on the count. So any count is just int max, and then a specific count is the specific count. And that's basically that. So that's our basic scanner here. We have an open ticket here for structure-based matching, and that's going to be more in line with people basically copying and pasting different libraries that we know were used for malicious purposes, and they are consistently formed in the same way. For example, structure matching here. So there is this Windows registry file that I've seen pasted in malware every now and then. And because it's just pasted and no one wants to like change anything, you're always going to see these values in these order. So if we had a structure-based system to match for the actual like layout of this code here, like fields in this order with these constant values applied, immediately red flag. There's no reason why Java code should be messing with a Windows registry. So that's what structure matching will be for. There's more information in this ticket if you want to read that. So if you want to contribute that, go ahead, read the ticket, and just address it, make a PR, and let us know when that's done. We'll take a look at it. And that's it for the standard static analysis scanner. The next thing we have is the dynamic scanner, and that's here. Now, this is by no means anywhere near as complete as the static one. Not to say that the static one is done, it isn't, but in terms of doneness, This one is I just I put into like a few hours of work today, and that's about it. So the way that this one works is relatively simple, at least in terms of the scanning like control flow here. So you pass in your model, same way as before. We create a results that you'll feed into. Then we create the SSVM context. This is just a wrapper for SSVM stuff. You don't really need to think about what's in here. I mean, except for this comment, this is a massive to-do item. But anyways, for control flow, the way that this works is that we have this interface here, the entry point discovery, and this is going to give you the list of common entry points for common like modding frameworks. So for instance, bucket plugins, this is just an easy example. The way that this would work is that the entry point discovery gives you the model and the SSVM context. You really only need the model though. Ideally, what the implementation of this would do for bucket, it would scan the classes for things that define a class that extends or implements the plugin interface type and defines a on-enable override. Then the entry point or a entry point would be added to the list that was returned that is the on-enable. So then when our scanner activates, it says, oh, there is a on-enable bucket plugin entry point that I need to start at. So it's going to start scanning with that entry point. So it's going to invoke that, and the stuff that we have defined in here will actually handle the matching stuff, but that's a to-do item. Now, obviously, a bucket plugin, the onEnable method is not going to call every other method in the program. There's things like, event listeners, there's utility calls that are called from different places. They're not going to cover all of the code dynamically if you just call the onEnable method. So what we do then is we have this other interface here, and the way that this is supposed to be implemented is that it will keep track of what is covered. We'll likely expose that in the SSVM context. Essentially, we will keep track of what code has been executed and what code has not been executed. And then, in a deterministic way, we will say, this is the next method you should call to cover the maximum amount of code. For instance, if we had a bucket plugin that had a bunch of utility methods that are small, and then a few event handlers, but those event handlers call the utility methods, we would have the coverage system here. We would have it prefer creating entry points for the event handlers because more code can be executed in a single execution if we start there versus if we start in the utility code. Because if we start in the utility code, we only execute that one method. But then we have to jump back to the other utility method and the other utility method and the other utility method, and then all the methods in the listener class. Whereas if we started with the listener class and the methods there, the event listener methods will be using the methods in the utility class. So executing from the event listener will eventually call those methods anyways. So that way we don't have to create as many entry point objects. So to summarize that kind of ramble, this will be an algorithm that determines the most amount of code covered per method, and then it will select the method that allows you to execute the most code. And then it will continue to do so until there is no code left that has not been executed, unless the code that is left cannot possibly be executed. In that case, it's dead code. It doesn't even matter. And that's handled here. So the way that it works is it'll continually ask for new entry points. And that's where I was saying it'll just continually say, okay, this is the next thing you should call. This is the next thing you should call based on what is the most active in terms of like what will be the most complex call that covers the most. If for some reason you get the same thing twice, we'll short circuit and say, the thing is, looping. We don't want loops. Just stop. And then if there is an exception such that the entry point that is provided to us can't be loaded for some reason, then we stop in that case too, and then we update the tracking so that this condition works. Once that system is done giving us data, so this while loop stops, we are done, and the sync builds the results. So that is effectively the entire project right now. I'm sure I missed something, maybe some minor details, but I can probably cover those at a later point. I think, yeah, I'll go over the util package actually. Nothing major here. This is a utility thing for other stuff. This is optimizing so that we don't recreate patterns over and over and over. This is some serialization utilities. And this is also another data util type. The last thing is this instruction strings, which is used for creating this part. So the part that comes after the opcode, the arguments. Now, my plan is to use a third-party library like JASM, which we use in Recaf. That way, if you have Recaf as like an analysis tool, you can just copy and paste out of it to make your signatures. If this is the case, we may even make like a handy little utility. You just select some code in Recaf and say right-click, export as signature. It could be something as simple as that. But anyways, if we use a common library in our analysis tools like Recaf and our tool here, easy integration. They should represent data the same way. So yeah, and that's a tutor item. It's just, I haven't pulled in JASM yet. There's some large-scale API changes going on in JASM, and I'd like to implement the new API out of the box rather than implement the old API and then have to start over when the new API is released. So the stuff still works due to the way that this is used because we have a null check here. So yeah, that's that. Test cases. Ideally, everything is covered in tests. So we have some additional utils here and here. You don't really need to think much about these. We have 2 test classes so far. This one is just for serialization. This makes sure that the this data type here, the deserializer and serializers work as expected. So we have wildcard support, multi-wildcard support, per numbers, per count there again. The basic thing that I showed before with arguments, the multi-instruction block, that kind of stuff, and then deserializing and serializing the model type itself. So that's that. And then we have the instruction matching tests. So the example that I was showing before with this file here is actually based on the example code in the test fixtures directory. So here we have a simple call to exec that opens the calculator. Here we have the same code, but it uses a variable in there. We have the same thing, but it's using a field. And we have the same thing, but it's using a object. So the type is not known until you cast it. And if you notice, 1, 2, 3, 4, 1, 2, 3, 4. These signatures correlate with each method. And if you were to run the test, run it with debug and hit a breakpoint here, we'll wait for Gradle to spin up because I just opened IntelliJ and it's not done that. Bam. So we have 4 results, and you can see there's one in Calc 1, 2, 3, and 4. The results are always going to be sorted order because it's a navigable set, because we're doing results.detections, which is just a navigable set of all detections and the results. And what we do is we make sure that there is a match for Calc 1, 2, 3, and 4. We do that by iterating over the detections and removing them from the set. And when we iterate over all the detections and do all the removals, the set should thus be empty. So if we jump down to here, you can see the set is empty because the remaining matches are gone. We've removed all of them, and the test passes. See, test pass. Running that again, you can see in the API here for these detection models, you were actually given a programmatic way to access information about the methods, the class, and the model source that it's from. So I can demonstrate that real quick. Detections.iterator.next. So let's do path. So assuming you have a path, it's going to likely be a method path element for any of the instruction scanner stuff that we were just discussing. For the dynamic stuff and the structure things, the paths will be different. But all you need to do is just check if it's an instance of the thing that you want. So in our case, method path element and then the thing. So what you can do is you have access to the method name, you have access to the method descriptor, and if you want access to the class, you have .getClassName, and you have source for the where the actual class is defined in your model. And that is handled in the path type here. We have a flexible path model, so all the data is accessible, and we use the parents to get the parent part. So a method has a class parent has a source parent, and that's basically it. That's how the path system works. The thing is navigable as an API, and we will eventually make different output forms for this in JSON, HTML reports, and command line output. So I think now I'm done. One little once over. All the packages has been done. Output. I mean, that's the stuff that's, yeah, I've been over that for the most part. Yeah, that's basically it. So this basically concludes the developer section of this video. So if any of this is of interest to you that you want to contribute to, please feel free to. I'm pretty busy as is, so getting the base out of the way, I wanted to do this so we can kind of be on the same page off the bat moving forward, and we can kind of like architecture agreed upon way forward from here. But yeah, most of the issues I think will be readily available on GitHub in a way that's explained well enough that you can kind of like get going on your own. And if there's any details missing, feel free to hit us up on Discord. I'm Cole E. I work on Recaf and a bunch of other projects, and I'm on basically all the reverse engineering Discords for Java stuff. I'm in the MMPA Discord. I'm in the Quilt and Fabric Discords if you want to hit me up there. Anywhere works. Any of the other developers, so Ned, for example, you can find Nerd the Ned on the MMPA Discord as well. So feel free to reach out to either of us, and if you have any questions, we'll probably get back to you relatively quickly. At least I will, because I know I'm terminally online. But anyways, that is the end of the discussion on the Concoction project in our current state and how things work and what we're looking for going forward. I hope you can find some of this stuff useful, and hopefully the project actually goes somewhere. Later. Bye.